Hello everyone, welcome to the TQC Seminar series. And today we're honored to have Catherine Meusburger to give a talk on the title of the talk is Dijkgraaf-Witten TQFT and quantum double models with the defects. And yeah, Catherine, please go ahead. Thanks.
So first, thanks to the organizers for having me talk here. So the work I talk about is joint work with João Faria Martins from the University of Leeds. I'll give a brief introduction to Dijkgraaf-Witten TQFT at the beginning, then I explain about defects, and then I go on to talk about our work. And it should be noted there's a huge body of work on Dijkgraaf-Witten TQFT. Well, originally Dijkgraaf-Witten, then there was a formulation by Fried and Quinn. Then there's more recent work, especially concerned with defects and extensions. So there's a lot, and I will not always be able to give the full list of citations. So just very basic, what is this? What is a Dijkgraaf-Witten TQFT with defects? Well, so a three-dimensional TQFT, and I'm only going to talk about 3 dimensions, is a symmetric monoidal functor from some 3-dimensional cobordism category into the category of vector spaces. So in this cobordism category here, the objects are closed 2-dimensional oriented surfaces, and the morphisms are equivalence classes of 3-dimensional manifolds with boundary. And the boundary includes the boundary is identified with the surfaces. Functor means essentially this is compatible, yes, with gluing, and it assigns to each surface a vector space and to each 3-dimensional manifold with boundary a linear map. Functor has compatibility with gluing, and that it's symmetric monoidal just means it's compatible with the disjoint union of manifolds, so it sends that to the tensor product of the vector spaces and tensor product of linear maps. So this is a 3-dimensional TQFT, and a 3-dimensional TQFT, among other things, are of interest because they give you 3 manifold invariants. That is simply if you consider a closed 3-manifold, considered as a cobordism between the empty manifold and itself, then you get a number, and this is a manifold invariant. Okay, so this is ordinary 3-dimensional TQFT. So what is different in a defect TQFT? So in a defect TQFT, you also have a symmetric monoidal functor, but what is changed is the cobordism category. It's no longer just closed surfaces and 3-dimensional manifolds with boundary, but the surfaces can be decorated with vertices and with lines. And the 3-dimensional cobordisms can be decorated with planes and with lines and with points. So this is no longer just a manifold, but these are stratified manifolds. And a defect TQFT takes this cobordism category with stratifications as the source. And if one considers a closed manifold with stratification, then this cannot be expected to just give an invariant of manifold, but it should give an invariant of a stratified 3-manifold. Okay, so why is this of interest? I mean, it's of interest, among other things, because of applications. So one thing one can do is apply this to condensed matter physics or topological quantum computing. And then one gets a description of defects in quantum double model and in Levin-Venn models. Another application is in CFT. I know far less about it, so I will not mention this much, but I know that other people apply it to conformal field theories. Yes, so there's a reason to be interested in this. And what did we want to do concretely? We wanted to give a geometric and gauge theoretical formulation of Dijkgraaf-Witten TQFT with defects. So the reason is Dijkgraaf-Witten TQFT without defects can be formulated in terms of geometrical quantities like bundles, gauge fields, and so on. And it can be described entirely in terms of quantities like that. On the other hand, in TQFT, usually one picks triangulations or handle body decompositions or something like that. and then defines the TQFT using these quantities. And especially in the presence of defects, one often needs diagrammatic calculus for higher dimension, for higher categories. And one describes this by diagrams, and one chooses triangulations and so on. So we wanted to see for Dijkgraaf-Witten TQFT, it's largely possible to avoid that. And then finally, we wanted some simple formulation where you don't have to work with, say, 20 triangles that are glued together in some way, and that should be very computable and also applicable to examples. Okay, so that was our motivation. And in order to explain the work, I'll first start with Dijkgraaf-Witten TQFT without defects in the formulation of Fried and Quinn. So you can think of the Dijkgraaf-Witten TQFT without defects as some sort of machine that takes as input a finite group. And what it gives you is a symmetric monoidal functor from a three-dimensional cobordism category to the vector spaces. Okay, how does this work concretely? Okay, such a functor, a symmetric monoidal functor, must assign to a cobordism a linear map between two vector spaces assigned to the boundary. So here X is the cobordism. We have two-dimensional manifolds as boundaries. We get a linear map assigned to the cobordism from the vector space for one of them to the vector space of the other. And if the manifold X is closed, has no boundary, this is just a map from the complex numbers to the complex numbers. So it's a complex number itself, and then you get a manifold invariant. Okay, so how does one construct these vector spaces and the associated linear maps? So there are various ways to describe them. One of the ways to describe the vector space assigned to the boundary is to say it's a free vector space. So this is my sign for free vector space, generated by isomorphism classes of functors from the fundamental groupoid of the surface into the group G, viewed as a groupoid with a single object. So here we have as objects, we have points, and as morphisms, we have homotopy classes of paths. Here we have as objects just a single object, and as morphisms, elements of G. So both sides are a groupoid, and we can see something like gauge field we can see as a functor between these groupoids. And then we take these gauge fields only up to isomorphisms, so gauge transformations on the boundary. And if the surface is connected, then we can just pick a base point, which is called X here, and then we can replace these functors by just group homomorphisms from the fundamental group of the surface into the group G. So these are the gauge fields, and the gauge transformations just become conjugation. So you have conjugacy classes of group homomorphisms from the fundamental group of G of the surface into G up to conjugation. And then you take the free vector space generated by this. So that's the boundary vector space. And this can be seen to be directly related to the quantum double model on the surface for the Drinfeld double of a finite group. So in the quantum double model, one has a sort of flatness condition for each triangle. So one takes the triangulation of the surface, and for each triangle, one has a flatness condition, namely that the group elements on two of the sides of the triangle multiply to the group element on the third side. And here the edges of the triangle are oriented, and if you reverse orientation, you replace the group element by the inverse. On the other hand, you also have gauge transformations. So if you have a vertex here with like some incoming and outgoing edges, and you have some group element associated to the vertex, then it just acts by left multiplication, by right multiplication, or by conjugation for a loop. And one can see in some sense that the fact that this is a functor from the fundamental groupoid, so it takes homotopy classes of paths, is reflected in the flatness condition. And the fact that they're only considered up to isomorphisms is reflected in the gauge transformations. And this is something that has been shown. Okay. Now we also need to think about the linear map that goes from the vector spaces for one boundary, from the vector spaces to sigma 0 and to the vector space for sigma 1. And such a map we can describe in terms of matrix elements. And we say that the matrix elements here is given by the functors from the fundamental groupoid of X, so the three-dimensional manifold now, into again the group as a groupoid with a single object. And this functor is supposed to be compatible with the gauge fields here at the boundaries. So it has to restrict to them on the boundaries. And it's again taken up to natural isomorphism. And these natural isomorphisms must be trivial at the boundary. Yes. And if we take a triangulated manifold X, just to make it a bit more concrete, then this matrix element here is simply the number of flat labelings of the edges with group elements. So flat means that for every triangle we have this condition that restrict to the appropriate boundary labelings up to interior gauge transformations. So gauge transformation like here, but only on the vertices that are not at the boundary. Okay. And again, if X, the three manifold, is connected and has a trivial boundary, then this is again just given by group homomorphisms, this time from the fundamental group of X into the group G up to conjugation. But here it's not the free vector space generated by those, but it's the number of such group homomorphisms. And if one looks in the literature, one can see that these gauge fields, so these functors that I always call A here, are somehow related to flat bundles or to discrete bundles on the boundary surfaces and on the cobordism X. And in this sense, you can formulate it without picking any triangulations or picking any base points. You can describe it in terms of functors. You can also describe it in terms of bundles. So that is the theory without the defects. Do you have questions?
I do. Yes.
Yeah.
So for this calculation for Zx, is X being assumed connected there or anything? So we have pi1 of X, and I'm just curious, like, if there's any subtleties with base points, like.
So here not, because the pi1 without a base point is just the fundamental groupoid.
Okay. Yeah.
So here, if there's no base point, like here and here, it's the functors from the fundamental groupoid into the group viewed as a groupoid with a single object. And that's precisely why we picked them, to avoid issues with base points. And if we impose connectedness, we can go to the fundamental groups.
So if X has two different connected components, then it's kind of like G conjugation on each of the connected components separately? Okay, thank you.
Exactly. But if you want to avoid to make all these case distinctions, you can just talk about the groupoid.
Great, thanks.
Yeah. So the groupoid is the categorical coproduct of the groupoids for each of the connected components. And because everything is supposed to be compact here, you don't have infinitely many connected components, just finitely many ones. Okay, if there are no further questions, I will go on. Okay, so I'll talk a bit about defects and explain what one means by introducing defects into the picture. So essentially, or as a slogan, one could say the defects are lower dimensional submanifolds that are decorated with higher categorical data. Which higher categorical data is the good one depends on what is the categorical data of the model without the defects. And in this case, I would say the categorical data is known also from the work, for example, by Kitaev and Kong, who studied it is for Levin-Venn models, and one has a clear idea what to put. Okay, So one needs to think about how to organize all these lower dimensional submanifolds of different dimensions into something coherent, and one needs to also think about how to label them with higher categorical data. An appropriate notion to organize the lower dimensional submanifolds is the notion of a stratification. And a stratification has strata. I'll explain this in a moment. And to the strata, we then assign different defect data. Okay, so what about the stratification? So here I only talk about oriented piecewise linear manifolds of dimension 2 or 3 with boundary or without boundary. And all of the manifolds are also supposed to be compact. Okay, in this setting, our notion of stratification is the following. So a stratification is always a filtration by certain subspaces. So we have one for each dimension, so x0, x1, and so on, and then it stops at xn, where n is the dimension of the manifold. So if we're in dimension 3, we stop at x3. If we're in dimension 2, we stop at x2. And all these closed subspaces, they're called the skeleton, and they're supposed to be closed. So that's not yet a stratification, that's a filtration, and a stratification is a filtration subject to more conditions. So if we have a filtration, we have a notion of strata. So the K-strata, they are defined as the connected components of the K-skeleton minus the K-1 skeleton. And typically one imposes certain conditions on them. So the condition we impose is that they're oriented piecewise linear K-manifolds. So the K in the K-stratum gives you the dimension of the manifolds, and they can have a boundary, and the boundary must be contained in the boundary of X. Okay, so these are the strata.
Question here.
Yeah.
Here, do you don't require these manifolds? This K strata are both disks in general. They're just manifolds. So
they have to be oriented piecewise linear K manifolds and compact, of course. We don't require them to be disks, but that's of course one possible case.
I see. Okay, so this filtration doesn't have to arise from a cell decomposition?
No, it doesn't. And I mean, there's a reason why we don't want that, because we want to also treat examples where this is not the case. I mean, if you work with the triangulation, of course, you get the cell decomposition and so on. But we also want to consider a general case in the formalism that doesn't put a cell decomposition or a triangulation in from the beginning.
Okay, yeah, thank you.
Okay, and we have more conditions on the strata. We have a condition that one could call locally conical. So this is like the piecewise linear counterpart of Lurie's locally conical, but with restrictions. And we ask that it's oriented, and we ask that it's framed. So this is somewhat hard to explain. So here I've given pictures. So locally conical means that the strata have like defined neighborhoods that are given as like R time or RK times some stratified sphere of an appropriate dimension. So here it would be R times a stratified circle. So here's the stratified circle with all these dots, and R is the direction of the line. Here we have a codimension, so I write it a codimension next to it. So this is a codimension 1 stratum. So here we just have a stratified dots, basically. So the neighborhood it always looks like we have like a ball, and this ball is divided in 2 halves. So in codimension 1, we have like each slice here needs to look like a stratified circle here. And then we have the direction of the stratum. And in codimension 2, so that would be a vertex, the neighborhood is, here we have a stratified sphere. And these arrows in the picture encode our notion of orientation. So for each defect of codimension 1, we get a normal vector that one sees here. This should have been codimension 2 and 3. Sorry, 2 and 3. Yeah, for each codimension 1 defect, we have an orientation, like here it's an oriented line. And we also have for the lines to have a framing. So we have one distinguished local stratum that is marked. So they're not supposed to twist them when gluing.
Catherine, and there's a question by
Yeah.
Eric.
Yeah, I have a couple questions. So does this data, it sounds like it's implying the data of like a normal framing. Is that correct? Of the strata?
I think so, yes, for the codimension 1 strata and for the, yes, in some, yes. So for the
Okay.
0 strata, not, but for the codimension 3 strata, not, but for the codimension 2 and codimension 1 also.
Cool. And then, so I'm also a little unclear, maybe you said it and I didn't understand. So when you say that the K strata or oriented PLK manifolds with boundary, can you say like that middle example there, the codimension 2 example?
Yeah.
If I look at the 2 stratum, so it's like those colorful 2 cells?
Yes, these are the 2 strata, yes.
But so I'm a little confused what you mean. Like if I remove that red 1 cell.
Yeah, so the boundary, so I should have said this. So basically we have a boundary that you get when you remove the things. And that's the boundary. But what I mean by this is they have in the boundary like a distinguished part of the boundary that hits the boundary of the manifold. Like for example, the manifold could end here, and then you would here have a boundary, like the intersection of the stratum with the boundary.
Okay.
Yeah. So this is a bit unclear because it's compressed.
So yeah, but like if I look at that green 2 cell, once I've removed that red cell, you're not thinking of that green 2 cell as having a new piece of boundary where the red used to be?
That's precisely I'm not. So I mean, of course they have strata because you're cutting up the skeleton. The strata have boundaries because they're cutting up the skeleton, and they have like something that we call the boundary of the stratum, and that is a distinguished part of the boundary. So basically, if here your 3 manifold ends, then this is all boundary, and we call these things boundary strata, and we distinguish them from these parts. They're not called boundary.
Okay.
Yeah.
Thank you.
Okay. Okay, and now, so I mean, there can be many strata of various dimensions, and now one needs to think about how to assign defect data to the strata. And the rule is always, when you have codimension 0, you think of this as gluing together different theories of the type you're considering with like a wall between them, the defect. So for codimension 0, you're supposed to have the same data as before, but various assignments for the different strata. So in codimension 0 strata, just get finite groups, like in Dijkgraaf-Witten without defects. But you can have more than one finite group. Okay, and the codimension 1 strata, they get finite sets with group actions. So here I've drawn again a codimension 1 stratum. So here we have a finite set M, and we have 2 groups that are neighboring the set. These 2 groups can of course coincide, but generically they can be different. And we ask that both groups act on the set M, this one from the left and this one from the right. Okay, how do I know that this is the most appropriate defect data? So it's not the most general defect data we can consider. We could consider already in Dijkgraaf-Witten TQFT twisting with the cocycle, and we could also here consider twisting with the cocycle. But up to that we do not twist here, it's the most general data. And this comes essentially from work in the context of condensed matter physics and from the fact that so this work identified the appropriate defect data for Toralf-Viro and Levin-Wen and quantum double models, essentially. And here we know that we have to have a special case. So if we only want to consider Dijkgraaf-Witten, we have to see it as a Toralf-Viro, and this corresponding data has there been classified. And up to the fact that we do not consider twisting, this is the most general data. Okay. So now what to do in codimension 2? To a codimension 2 stratum, like this red line here, we associate a representation of an action groupoid. So first, what is an action groupoid? an action groupoid you get when you have a group G acting on some set M. And the objects of these groupoids are the elements of the set. And the morphisms are group elements, and they are viewed as morphisms from M to the image of M under the group action here. So this you can construct in full generality for group action of the set. Now we want to assign such a representation of an action groupoid to this line here. So how do we build the action groupoid? Well, we consider a small neighborhood of the stratum, and then we look at the defect planes that intersect the small neighborhood, and we just take the product of all the sets associated with these defect planes. So here M, N, and P, and we take the product. And for the group, we do the same with the three-dimensional regions. So here we have K, H, and G. If we go in a small neighborhood that intersect this, and we take the product of this group, and we let each group in this product act on each element here in the way given by the group actions for these planes. And this is our action groupoid, and then a representation of such an action groupoid is just a functor from the action groupoid to the category of vector spaces. And I'll give some examples of such functors later. And finally, in codimension 3, we will then get intertwiners between action groupoid representations. So intertwiners here are just natural transformations, but one needs to be a bit careful. So here we have a situation, we have one edge here, we have one edge here, and one edge here, and they meet at this vertex in the middle. So each edge comes with an action groupoid and the action groupoid representation, but what we need for this vertex is like we need to combine the action groupoids of all the edges. So we do the same thing as we did here. We collect all the defect plane, the data of all defect planes that are in a small neighborhood of the vertex. And we connect the data of all the three-dimensional regions that are also in a small neighborhood of this vertex. And so we may have certain defect planes that are not incident to some of the edges. Like, for example, here F1 has only P and M, but there's also N. And we take the big action groupoid for all the planes and for all the regions, and then we add projection functors that project on the action groupoids for the defect lines. And once we projected on the action groupoid for the lines, we can just apply here the representations that are associated with the lines, and then we can consider such a natural transformation between the functor for F1 here and then the tensor, the pointwise tensor product of the other two. So this is essentially the defect data. And in codimension 2 and 3, it doesn't get much more complicated if you do twisting, but we didn't want to do this in this work. Okay, so you know what to associate to the defects and how to treat the defects mathematically. And then you can define a defect TQFT in a way similarly to an ordinary TQFT. So you have a defect cobordism category where the objects are stratified closed surfaces plus an assignment of appropriate defect data to each stratum. And the morphisms are then equivalence classes of stratified cobordisms plus an assignment to defect data to each stratum. And for the inclusions of the boundary, now the defect data on the objects must match the defect data on the three-dimensional cobordism. And gluing is also only with respect, so that the strata must match and the defect data on the strata must match. And in case of one-dimensional things, also the framings and the orientations, of course. And the tensor product in this defect cobordism category is again just a disjoint union of manifolds. Okay, and of course, if you have a defect cobordism, so if we have only a single stratum, then you have a label G, which is some finite group. And then you get back just the ordinary Dijkgraaf-Witten. cobordism category, plus a choice of the data. So there it doesn't matter. You can say Dijkgraaf-Witten is just the cobordism category, or it's a cobordism category to get together with the choice of a finite group. Okay, so this is the defect cobordism category, and then a defect TQFT can be defined as a symmetric monoidal functor from this defect cobordism category into the category of vector spaces. This is a definition one can make. The problem is how to find such functors. Or how to construct them. And one possibility to construct them is from triangulations, cell decompositions, and so on. But that's not what we want to do. And we want to construct them in a more geometrical way, and also in a way that is closer to gauge theory. Okay. I think now is maybe time for the break. Is that okay?
Yeah, sure.
I mean, it should be 30 minutes. That's roughly.
Yeah. Perfect.
Is there any
questions?
Yep. So here, it seems the Dijkgraaf-Witten TQFT without defect can be defined on unorientable manifold. Is that right? But here for the defects, I can see here you do need the orientation.
We need them to a various degree. Like basically for the codimension 1 defects, it's not strictly necessary, because if we have a set with a left action of one group and with a right action of another group, then of course we can also say we have right actions of both groups by simply taking an inverse. But for the codimension 2 and 3, it's necessary. And I think it might be also necessary for codimension 1, because for example, you could try and take something. Okay, so this would be an example what you could consider. You could consider a Möbius strip. You could consider a Möbius strip with a single defect line in the middle. Then, like the two strata, like the strata would be orientable, because you have one stratum that would be, if you color everything here, this would be just that. So you have one stratum, but because you have removed the middle line, it's orientable. It's like when you cut a Möbius strip in the middle. So the stratum would be orientable, but still here you would get problems.
Sorry,
but this is more like an explanation why we need the framing than why we need the orientation. So I would say here it's still quite mild because of the simple data, and also for the vector space data, you can take duals and you will get no problems if you're just taking vector space duals. So I don't know if there's a generalization of this to non-orientable, like with the full defect data. I think there could be, but it will certainly be much more involved in how you treat all this data and how you pay attention to certain details.
Okay. I mean, also, I think it's interesting, but maybe okay, I guess it's a little bit confusing to me, is that even in the case without defects, we know for example, the Kitaev quantum double model, right? You need orientation. I think you need orientation on the surface to define the Hamiltonian. But on the other hand, the Dijkgraaf-Witten TQFT, as you stated here, it seems there's no requirement on orientation. Like the manifold doesn't have to be orientable.
I think you can consider bundles on unorientable manifolds, and that's why it works. I think for the Hamiltonian, you need the orientation because you need to talk about like the triangles and like when you impose a flatness condition on the triangle, you have to take it like you have to have some relation between the orientation of the edges and the orientation of the triangle. And the orientation of the triangle comes from the orientation of the surface. So it might be really something that is connected to decomposing it into triangles. But I don't know the full answer. So in principle, group homomorphisms from the fundamental group into some group G, you can always have them. That's not a problem.
I see.
And I think also like homotopy invariance you can also have. So maybe in the Hamiltonian you could define it in a different way, like not by taking group elements, by not taking products of group elements, but instead saying that some compositions of edges that are homotopic can be must have the same element. So I don't know, but it's a good question.
Yeah, sure.
So I don't know how to do this construction for the unorientable case. And the main reason is because so many things would get more complicated. So I would be overwhelmed by the complicatedness, but I don't know if it's impossible.
I see. Yeah, certainly I think yeah, I think since you need locally the frames, I think without a global orientation, I'm not sure if you can get everything in a consistent way.
Yeah. Yes, I think so too. And
right. Are there any? I mean, I guess I have more questions, but maybe I want give other people a chance to ask questions. Are there any questions for Catherine this moment?
I mean, I wanted to ask, so governing all the additional data you have on the manifold seems a quite technical task. Is there some additional structure which can do this for you, or
organizing this data?
Yes, and dealing with all of these additional data, especially.
That's the second part of the talk, how to organize this.
I see. Okay.
Basically, how we organize it concretely. I mean, I don't know what you mean, if you mean that there's like some categorical nerve behind it or something. I mean, there is a categorical structure behind it that is basically a tri-category. Now you could argue, is a tri-category an efficient way of organizing this data or not? So did you ask about that?
Less on, I guess this would more address the algebraic side. I'm really mean on the topological side. If you want to say, well, the stratified manifolds are in some sense isomorphic, then I guess you have to check a long list of relations and transformations.
If you want to say that they're isomorphic, stratified isomorphic.
And then check that your invariant does not depend on a representative in the isomorphism class. So I don't know how this works and whether you have.
Okay, I can say about this later in the talk.
Yeah.
Essentially, we use quite strong tools. We use Kahn extensions, for example, and then okay, but I'll get to this later.
Yeah, but this answers the question. Thanks.
Okay.
Are there more questions at this stage? Remember, there are some works. I guess maybe it's also Sebastian's work. I'm not sure. On the non-summa simple Kitaev model. Is that your? So is this Catherine? Is what you are talking about here? Is it still in the semi-simple framework? Can you make a comment?
Yes, I mean, how should I say? So I could write down the data in a more categorical way, then you would see this. So then I would have, instead of the group G represents really the fusion category vec G. the G times H offsets that corresponds to vec G, vec H bimodule category. The representations of the action groupoids, they correspond to bimodule functors. And the intertwiners to bimodule natural transformations.
Okay.
So this is it's you're starting out with a finite starting out with a fusion category. It's a spherical fusion category, and it's as semi-simple as it can be.
Okay. Yeah.
Yeah, I mean, this is what needs to start somewhere, and this is already complicated enough.
Yeah, for sure. Yeah.
But I mean, it's of course a good question.
I don't know much about the non-summa simple setup other than I've seen the titles, sometime. So I just wonder if if there is a non-summa simple version of the defect theory, but I guess it will be more involved in the construction. But yeah. Oh, we can talk.
Yeah, so I don't know. I'm certain that probably this construction will completely not work. I mean, of course, you could try to work with topological groups, but already then you know that you're replacing like the ground state, basically, or what is assigned to the surface. You're replacing it with a complicated moduli space of flat connections, and this will be very hard.
Okay.
So I think this is not one of the things that this can achieve.
Sure. Okay, are there more questions? If not, I guess maybe we can continue.
Okay, just wait a moment.
Yeah, sure. Yeah, take your time. If you need to take a break, that's fine too.
No, I just wanted to switch my mobile phone off. Sorry about this.
Yeah.
Okay, we can continue.
Yeah, go ahead.
Okay. So now we want to construct really a defect TQFT without using diagrammatic calculus for higher categories, without using much triangulations and so on. And our construction was really from the basics, and the first step of the construction is something we call gauge groupoids. So we assign to the three-dimensional manifolds and also to the boundary surfaces, we assign a groupoid. And it's an action groupoid, so that's this notation means we have an action groupoid, we have a set of gauge fields, and we have a group of gauge transformations. And this is assigned to the cobordism and also to the boundary surfaces. And it makes use only of the defect data of codimension 0 and 1. So only of the groups and of the sets with the group actions. So how do we define this, or what is it concretely? So I'll say first what it is concretely and then how we get this. So what a gauge field is, so an element in this set here, is essentially an assignment where we give to each codimension 0 stratum a functor from the fundamental groupoid here. So the fundamental groupoid of some space associated to the stratum into the groupoid with the single object and the group isomorphisms. So this is essentially what we did in Dijkgraaf-Witten TQFT without defects, but here we have to say what the space is, and it's a bit subtle. So it's not the stratum itself. It's also not the closure of the stratum, but these spaces denoted with the hat are the spaces you obtain by cutting the n skeleton along the n-1 skeleton. So they're not open like the strata, but they're also not a skeleton. And I'll explain this in examples later. Then to each codimension 1 stratum, we assign a map simply from the associated space obtained by cutting along the codimension 2 strata into the set that is associated with the codimension 1 stratum. And these assignments have to satisfy a condition which can be read as some sort of parallel transport condition. So here I've drawn a codimension 1 stratum S and the associated space S hat. And then there are two codimension 0 strata here called T and P, T and R. And the condition that one has is that if one has a path on this space for the codimension 1 stratum, here this path delta, from some point x to a point x prime, then this path also belongs to the codimension 0 stratum T and R. And these functors here assign to this path a group element, one group element in the group for T and one group element in the group for R. And we then ask that the value of this map AS on the surface at the endpoints x prime and x, that these values are related by the action of the group elements that are associated to the path, here and here. And one acts on the left and one acts on the right. Okay, so this is what we call a gauge field. So one recognizes here one has the gauge fields for Dijkgraaf-Witten TQFT, and here one has the one for the codimension 1 strata, which are kind of like defects in between the gauge fields on which the gauge field act. Okay, what about the gauge transformations? They are simpler, they are just an assignment of a map from the space for the codimension 0 stratum into the associated group for each codimension 0 stratum. So the gauge transformations basically live here and they live here, but they don't live here essentially. And on the functors for the codimension 0 strata, they act like one would expect. So we have a path delta now in the codimension 0 stratum space. And they act by left multiplication with the element at one endpoint and by right multiplication with the element at the other endpoint. So like one would expect on a graph gauge theory or something. And they act similarly on these maps that are associated with the codimension 1 stratum, just that we don't, we have only one point x here, and we act on it from the left and we act on it from the right with the two different groups. And again, so here we have the group GT, here we have the group GR, and here we have the set MS. So this is like a geometrically intuitive description of what a gauge field could be in the presence of codimension 1 defects. So where does this come from? So this is not a guess, but it comes from a quite complicated construction, this gauge groupoid. And it's a categorical construction. Basically, we have three things that we have to take into account. So our stratification has combinatorics, like which strata are incident to which strata of higher dimension. Like we could have a point, and then we have an edge, and the point is basically incident twice to the edge, once here and once here. And this is like the combinatorics of the stratification. And we encode this in a graded graph. So that's a graph with a degree associated to each vertex so that the edges always raise the degree by 1. And if we have such a graph, it's a directed graph, and then we get immediately a free category generated by the graph. And on the other hand, the strata also have topology, and the topology is not trivial for the strata. And the topology is organized into a functor from this free category associated to the graph into the category of groupoids. And finally, the strata also have algebra because we have defect data associated to the strata. And that will give us another functor from the free category associated to the graph into the category of groupoids. So I'll sketch this and I'll say something more about the construction first. So here I've said how the gauge field is constructed. So basically we have these two functors, T and D, And we put them into an enriched Hom functor. So we have a functor Hom that takes values in groupoids. And then we take the end. This is like something like making a natural transformation. And because this is constructed with an end, we get functors for each stratum. Let's call the stratum U. We get a gauge groupoid. And we get a functor that goes from the big gauge groupoid of the entire manifold to the special gauge groupoid for the stratum. And these functors interact in a good way. Like, for example, if one stratum is incident at another, then you can compose the projection functors in various ways, and you have certain projections between the different groupoids. And this comes all from the end construction here. And that's quite a powerful tool. So I'll only sketch this description here, but it was also a bit to answer the question. So how does this look like concretely? So first, the graded graphs here. So our graded graph has edges. The highest edges are the ones for codimension 0, then codimension 1, codimension 2, codimension 3. The vertices we have here, and then we have edges that always go one level up. And that we can do that is part of our assumptions. We have assumed from the beginning that each codimension 1 stratum has an incident codimension 0 stratum, and so on. Yes. So the vertices of these graded graphs are the strata. The edges describe the local incidence of the strata. And the degree associated to a vertex is basically the dimension or the codimension. So what do I mean by this concretely? So this here is an example of a stratification. So we have a two-dimensional surface. On this surface, we have a codimension 1 stratum, the edge here in blue. And on the codimension 1 stratum, we have a codimension 2 stratum, this defect vertex. So in this picture, we have two codimension 0 strata, the left and the right. So we have two vertices on the top level. Then we have one codimension 1 stratum. So that's the edge, that's here. And this edge can be included into the right and into the left. So we have an arrow here and an arrow here. Then finally, we have a single codimension 2 stratum. That's the red dot here. And this can be included into the edge in two ways, like for this edge end and for this edge end, because the edge is a loop. And that's our graded graph that we assign to this. And as I said, we consider only incidence of strata to strata of the next dimension. So of course, this is also incident to right and to left, but we do not consider this because we encode it in paths. Okay. And how about this functor t then? So this functor t should assign to each vertex in the graph, so to each stratum, the fundamental groupoid of the associated space. And this associated space was obtained by cutting the k-skeleton along the k-1 skeleton. So the boundary of the stratum is in there as well. It has a boundary, it's not open. And the edges here, they give us continuous map that describe how we glue a lower dimensional stratum to a higher dimensional one. So this glues the k-1 strata to the k strata. And this defines a functor. So how does it look like in the example? So in the example, the left and the right, the spaces associated to the left would be all this, but including the edge. And the space associated to the right would be all this, including the edge. So here we can take the closure of the left and the right. And then we take the fundamental groupoids. Okay, but what about the space of the edge? Well, I have to cut the 1 skeleton here along the 0 skeleton. So I cut the edge at the vertex and I obtain a closed interval. So the stratum itself would be an open interval and the closure of the stratum would be a circle. That's not what we are doing. And for the point here, I get as a space a single point, and the fundamental groupoid of a single point is also the groupoid with one object and one morphism. And then here we have obvious inclusion. So here the single point is included into 0 and into 1. And here this interval is sent to the edge here, which is included in the boundary. And this is, of course, not injective because the two endpoints here are mapped to the same point here. And finally, we have a functor D that describes essentially the groupoids made from the defects. So what we do for each stratum T, we take the product of all codimension 1 strata at T, and the product of all codimension 0 strata at T. Here we take the associated group, and here we take the associated set. And if we have a lower dimensional stratum, S, that is incident to a higher dimensional T, then we get a canonical functor that projects from the groupoid for S to the groupoid of T. And in the example, one can see it here. So here, basically for left and right, it is easy. So these are two-dimensional strata. They are codimension 0 strata, so they just have groups and just have sets. So what we take here for left and right is the groupoid, is just the groups as a groupoid with a single object. Okay, this edge E is decorated with a set with an action of the group here and the group here. And the groupoid we assign to it is just the action groupoid for this set with the two group actions. So now what about the vertex? So for the vertex, again, we have two groups, one here and one here. But we also have two sets because the edge has two edge ends and we have two copies of we have one copy of the set for each end. So that's what we get for the vertex. And then what is associated to these arrows is almost canonical. So the upper arrow just projects here. We take everything on the single object in every object and just projects out the right group and keeps the left. On the other, on right, it's similar. And here, to go from here to here, we project out one of the copies of the set. So this is roughly what it works like in practice. And all the properties that we needed are proven with this description. So we have worked out the concrete pictures and so on. But really what is powerful here is this. Okay, was this roughly understandable?
Yes. Can't speak for everybody though.
Okay.
A short question. Does orientation play a role here, and is this encoded in the graphs?
The orientation plays a role in kind of identifying what belongs to what. But it doesn't play a role much in these groupoids, and it doesn't play a role much here in this level and the formalism in general. But you need it for kind of bookkeeping. So probably you could get around the bookkeeping here, and then you would get a more complicated bookkeeping, but I don't think it's genuinely needed much.
Yeah, okay, thanks.
Okay. So this is roughly how we construct these groupoids associated to the different strata. And now one is not just interested in by combining them for all the strata, we get this big groupoid here, which projects down to the groupoid for every single strata.
Sorry, one question.
Yeah.
From the topological point of view, is there, I think I didn't get if there is any notion of the puncture here.
No, there isn't really a notion of a puncture because we wouldn't want a codimension 2 defect that is not adjacent to a codimension 1 defect. So there will be a notion of a defect line on a like with defect planes incident to it, and there will be a notion of a defect point on the boundary surfaces between defect lines. But we don't allow, for example, a codimension 0 defect that just sits inside a codimension 3 defect. So we wouldn't allow, for example, just a ball with a single defect point inside, but on the surface we get defect vertices that can be like defect points.
Okay, I see.
Okay,
Thank you.
I'll come back to that later. Okay. So now one is interested in the properties of this assignment of gauge groupoids. And what we showed in our work is that the assignments of the gauge groupoid define a symmetric monoidal functor from the defect cobordism category into some category consisting of fibrant spans of groupoids. So I'll explain this a little bit. So here we have the picture, we have the cobordism X, and here we have the source, and here we have the target. And what it does, this functor, is it assigns to the boundary components, so to the surfaces sigma 0 and sigma 1, it assigns a groupoid, a gauge groupoid, and it assigns a gauge groupoid to X. And this comes together with functors from this gauge groupoid for X into the boundary gauge groupoids for both boundaries. What do these functors do? Essentially, they restrict the gauge field to those strata that are incident at the boundary. So this here is a span, as one can consider from the picture. You can also just take the picture for itself. It's like three groupoids together with two functors. And fibrant here means that the map that is induced by these two functors here, that goes from the big groupoid into the product of the boundary groupoid, that this is a fibration. This has some kind of physical meaning. It means that gauge transformations on sigma 0 and sigma 1 lift to the bulk. That means if I give two gauge transformation on the boundary surface here and here, then there is a gauge transformation in the cobordism that restricts those two at the boundary. Okay, the way how we prove this is pretty hard. So we considered, especially it's hard for the gluing of the stratified surfaces. So the gluing gives us various push-outs of graphs, and then we are taking Kahn extensions of the functors, and it's not easy really to describe. But this is really, we use categorical methods, and this would be pretty impossible to do just in a hand-waving way by a concrete description. And basically, because all the categories we use are nice and they're well compatible with push-outs or pullbacks, depending on where we are, and because we're using Kahn extensions, this worked. But this is a very difficult proof. Okay, so this is what we do with the gauge groupoids, but we still have the data for the codimension 2 and 3 defects. So the codimension 2 defects, these lines here, and their boundary endpoints, they carry representations of action groupoids, and the codimension 3 carry natural transformations between them. And what we could show then is that, like, the data on these codimension 2 and 3 strata, this defines a graph. And the labels on this data, so the representations here and here and here and the intertwiners here, they define a diagram for a symmetric monoidal category, namely the functor category from the gauge groupoid into the category of vector spaces. So in this category, we have as object functors from the big gauge groupoid of X into the category of vector spaces, and as morphisms, we have natural transformations. And how do we see that this is such a diagram? Well, here we have already a representation, but of a smaller action groupoid, namely the one for the edge. And here also, and what we do is just we project the big action groupoid for X on the smaller action groupoids for the strata with the functors we have from this end description. And then here we apply the representations here and here. And then we just take the tensor product over all the vector spaces here. So this can be viewed as a diagram for such a category. And what we can then show is that if we evaluate such a diagram, we get a functor from the boundary gauge groupoid into the category of vector spaces. So basically just collect all the representations at these dots here, tensor them together, and apply the resulting functor together with some projections to this groupoid here. And the same happens for the other boundary. So there we get also a functor, but from the gauge groupoid for this boundary here, into the category of vector spaces. Between these groupoids, we have the span that is the same as here. And what we can see is that all the codimension 0 strata then define a natural transformation from applying first this and then this functor F0 here. This is a functor to vect. So this goes from AX over GX to vect. And this here is also a functor. And we have a natural transformation between them. And with the categorical methods, we then showed that this defines a symmetric, this together, like the upper theorem and the second part, defines a symmetric monoidal functor from the cobordism category with defects into some category of fibrant spans of representations of groupoids. So that here in the middle is essentially the category of fibrant spans and of representations of groupoids. And then we combine this with another functor that goes from the category of fibrant spans of representations of groupoids into the category of vector spaces. So we constructed this functor in the fibrant setting, but it was also constructed before by Woike-Schweigert and by Trover. So they have constructed functors, so it was not also imaginative. And then if we combine these two functors, this here should be an evaluation. If we combine these two functors, we get a functor from the cobordism category with defects into the category of vector spaces. And that's a defect TQFT. Okay, so that's the abstract construction, but basically we wanted to apply it. And one situation where we wanted to apply it is also, for example, matter, but here I take a triangulation, and we have some labeling that assigns to each edge an element of a finite group G. And this gives us an extended space, a vector space, that is just the free vector space generated by this labeling. Then we have for every triangle, we have a sort of flatness condition that I mentioned before. So if we have group elements G and H here, and the group element K here, then K must be equal to GH. And this we can also see as a linear endomorphism of this vector space here that just multiplies with the delta function associated to this triangle. For each vertex, we have a notion of gauge transformation. So we have some edges with their labels here. And then we just left multiply the incoming edges with some element at the vertex. So G is here at the vertex. And we right multiply the outgoing edges at the inverse. And then we can consider the linear subspace of this extended space that consists of those spaces that are invariant under these phase operators that implement the flatness condition by multiplying with deltas, and that are invariant under these operators that perform a gauge transformation. And this is some linear subspace of H, and this is the protected space of the quantum double model. And what one can show quite directly is that this protected space is nothing but a free vector space generated by the group homomorphism from the fundamental group into the group G up to conjugation. You just contract the edges of your triangulation until you're left with a single vertex and a lot of loops, and then you have that here. And this is also the vector space assigned by the Dijkgraaf-Witten TQFT. So what do we do with defects? So now we consider domain walls, so codimension 1 defects, and domain wall junctions, codimension 0 defects. So here we have a little domain wall. We say we put on the right a group G and on the left some group H, and the domain wall itself gets labeled with the set M. And because the domain wall is oriented, we orient all the edges that intersect the domain wall in the direction of its orientation. And then we get mixed triangles that have 2 blue sides and 1 black side or gray side. And here we can play the same game. We can assign to each triangle a flatness condition, but instead of saying certain group elements are equal, we just say that these 2 blue elements are related by the action of the gray element. So here M must be equal to the right action of H on N that we see. And here we have M. And similarly here we say that P is given by a left action of G on N. Well, and gauge transformations also work similarly. Just when there are some incoming edges that are colored and not black or gray, we just take the action on the set instead of the left or right multiplication. So here for the edges that are black, it's as before, left or right multiplication, and for the blue edges, it's left action, and for the purple edge, it's a right action. So we can define this completely analogously, and then we can say, we can also ask that, for example, a domain wall becomes invisible. So if we label a domain wall with the group G as a G times G offset, which means here we have group G, here we also have group G, and here we also have group G, then this is the same as having no defects. Yeah, then we can consider a domain wall junction. So there we have different defects coming together. In my case, it's 3, but it could be 4 or 5 or maybe 2. In this case, we have all edges oriented in the direction given by the domain wall. And here at the corners, we have the different groups. So we have only colored edges. Here we have the groups. And then we see by looking at the picture that we get an action groupoid. So we have to label this dot in the middle, the junction, by a representation of the action groupoid. So here we collect all the sets at edges that come into the vertex, and here we collect all the group that sit here outside at the triangle and go to the category of vector spaces. Yeah, this means to each such triple of labels here, we assign a vector space. And to each triple of group elements here, we assign a linear map from the vector space of this label to the new label. And this is given more or less in the obvious way. So we have M prime. In this situation, we would have M prime is G acts on M, acts on H. And N prime, I think here we take an inverse. And N prime is K acts on N. And then we have G inverse, and P prime would be H acts on P. And here we would have the K inverse. So that's the action groupoid, and to the domain wall junction, we would assign a representation. Now one raises the question, can one also have trivial domain wall junctions? For example, if I make it transparent. So here I've just omitted one of the defect planes. So this is just the defect, a defect line labeled by the group. And here I have taken the same. So here we have the same set that labels both of them, but here we have an element M and here we have an element N. And we are just left with 2 groups, namely G and H. And here the label here that would correspond to no domain wall junction, just the domain wall, would be the trivial representation of the action groupoid. So we have an action groupoid with 2 copies of M and the product of the groups G and H. And what we can do is we can assign to these 2 labels either the trivial vector space, so the 0 vector space, if they're different, and if they're equal, we assign the vector space C. And then here we just have identity functor, that's not important. Okay, and given like our description of the domain walls and the domain wall junctions, we could now write down something like a protected space So here we would say we take the product over all the vertices of the group, the inverse of the group cardinality of the group that sits at the vertex. And we take the sum over all flat labelings. Then we take the tensor product over all the triangles. And then for each triangle, we take the vector space that is given by the labeling. So here we have the labeling M and P. We get a vector space, and we do this for each labeling. And that would be like the counterpart of the protected space. And that's precisely what our formalism would assign to the defect surface. So this works. And now, of course, one could make it a bit fancier. So like if I have M here and I have M here, I'm not obliged to put this trivial representation in the middle. I could put something more exciting, some representation of the stabilizer group, for example. And yeah, one could define this basically in full generality. And I can also work with a triangulation. And the edges where I don't want to have defects, I just label them with a transparent defect. Okay, but the question is now, this is very triangle oriented and very explicit, but it's maybe a bit impractical if, for example, I have very few defects, like in the example I've shown you before. So now I'll explain what this looks like in a different formalism, namely in the one I've introduced before. So now we take this as an example. So we have a genus 2 surface. Here we have a group GR. Here we have a group GL. Here we have a finite ZM. And here we have a vertex where we will put a representation. So we could say that's our defect structure. Now please compute the ground state of the quantum double model with defects, without giving me any triangles. Okay, so what can one do? So first one computes the gauge groupoid. And this gauge groupoid is valid or relevant only up to equivalence. So what we can do here from the beginning, we work with a base point, namely with this vertex V. And if we work with the base point, we restrict this groupoid to a full subgroupoid. And this restricted gauge groupoid then looks as follows. So then the gauge field becomes a triple. So we have two group homomorphisms, rho L and rho R. They go from the fundamental groupoid of left with base point V. I think here I should have put the closure of left and the closure of right into the group GL and GR. And in addition to this, I need a single element M of the set that is associated with the edge. So I need a single element M, and that's my gauge field. Now a gauge transformation is just a pair of group elements, one from the group of the left and one from the group of the right. And it acts on these group homomorphisms in the obvious way. So the group homomorphisms are conjugated with the appropriate element here. What does it do with this element M here? Well, it acts on the left for the left group and it acts on the right for the right group. So this would be my reduced gauge groupoid. Now to compute the vector space here, I would have to say which defect, which representation I put at the defect. So here I need a groupoid representation of this action groupoid. 2 copies of M for these edge ends and 2 copies of G for the left and right. And once I'm given such a representation, I can compute the vector space in a simple way without triangles. So how do I do this? Well, I have a projection functor from the gauge groupoid into this set. So I could write this down explicitly, what it does. So basically, here I have just one element M. This is too complicated. Maybe it becomes clearer later how I project it down. Basically, I assign, so here I have M, rho L, and rho R. And what I send this to is let's call this H left. This is rho left of E. H right is rho right of E. And then I assign to this M, and also rho HL acts on M and HR. So basically, what does this mean? I evaluate the group homomorphism rho L and rho R simply on this part here. That gives me the group elements here and here. And for the object, yeah. And what I do for the set here. So here in this groupoid, I need two elements. One sits here and one sits here. I'm given only one that is identified with one of these elements, but I know from my condition on the gauge fields from before, if M sits here, so if M is here, then I will have HL acts on M and HR inverse acts on M. So one of the two is already given, and this is what this projection functor does. And then I'm given a functor from this groupoid into the category of vector spaces. And if I compose them, I get a functor from the gauge groupoid into the vector spaces. And of this functor, I can take the limit here. And I can write down this limit explicitly if I want. So what I do is I sum over all gauge equivalence classes of triples. So such triples here, but only up to these gauge transformations. So I take one representative in each class. And then I apply this functor f that labels the defect vertex, and I apply it to M, and I apply it to the other element that is made out of M by going once around the circle to the other end of the vertex. And that's basically the ground state. And one can now look at special cases for consistency check. For example, if I make the vertex transparent, well, in this case, the M and this element must agree. So that means that M cannot be an arbitrary element of the set, but it must be a fixed point under this action. And then I get just the free vector space spanned by such equivalence classes of triples, where M is now restricted to a fixed point. And if I make the vertex transparent and I make the edge transparent, then it means G left is equal to G right is equal to M is equal to G. In this situation, I get back what I have from Dijkgraaf-Witten TQFT without the defects, namely just the free vector space generated by group homomorphism from the fundamental group into the group G up to conjugation. So everything here is consistent, and one sees that this formalism can be quite useful because here I can just start computing. I work with a suitably reduced gauge groupoid, but I do not have to take a cell decomposition or a triangulation or things like that. And this is because of the geometrical nature of this formalism. Okay, I think that's the end of my talk. Thank you for your attention.
Thank you.
Yeah, thanks.
Are there any questions for Catherine?
Maybe I should start by answering a question from before about the defect points or the punctures. So what I could do here is I could also label the edge here with the transparent edge. So if these two groups are the same and the edge is labeled by the same group, then I have a transparent edge. But the vertex could be non-transparent. And this would correspond to an excitation in the language of the quantum double model, or it would correspond to a puncture in the language of Chern-Simons theory. So what I could do here is I could pick like a conjugacy class in the group G and the representation of the stabilizer, and that would be suitable data that labels this defect vertex if the edge is transparent. And I think that answers the question about the punctures. And that's also the reason why we didn't consider this case separately, because it makes the formalism easier and we can add them back in by choosing transparent defects.
Mm-hmm.
And the transparent defects also give us a framing where it's needed.
Mm-hmm. Sure. Can you make a comment? I mean, I think there's lots of literature on the defects TQFTs.
Mm-hmm.
For example, I think that there are many papers by Runco, like Orbi folding and defects, TQFTs. But I think what they are doing is mostly on the Reshetik and Turaev TQFT.
Yeah.
And then
that's true.
what you're doing here, this is like more like the Turaev visual.
Yeah.
But at the end of the day, do you think they are still related by the double
Yes.
relation? Okay.
Yes. So I've never shown this, but there are like two distinctions. One is that it's Turaev-Viro and the other one is Reshetikhin-Turaev. You can see Turaev-Viro as a especially nice situation or an especially nice subcase of Reshetikhin-Turaev. So in that sense, we are just talking about that subcase because Dijkgraaf-Witten theory is in that subcase. And I think the other thing that is different is precisely what I said. We wanted to have the opposite, not so much reliance on diagrams. And what they often do is also making a new TQFT out of an old one by orbifoldizing.
Yeah.
And like orbifoldizing is like creating new data out of a given data. And you could apply this to Dijkgraaf-Witten TQFT, of course, and try to orbifold it. So I know that they did this with two group symmetries, and they got some examples of braided G-crossed braided categories. But this is like a different approach. So it's like a method to make less trivial categorical data. And here we wanted to make the most trivial categorical data to get a kind of geometric and picture with homotopes and fundamental groups and so on.
Yeah, for sure. Yeah. Yeah, very good. I think so. So here, this apparently, I guess, yeah, you mentioned this. You mentioned the case of twisted Dijkgraaf-Witten. So here, I guess you can still make the twisted version work, maybe with the introduction of more like a complicated relations and the constructions.
So I have a PhD student, Maximilian Ludwig. He's working on including the twists and also making this in a very nice way compatible with diagrammatic calculus.
I see. Okay. Okay. I mean, also, I guess there's also no need to restrict to the group case, right? I mean, in principle, it seems like you can use the Hopf algebra or even a weak Hopf algebra in the same setting. I mean, like, for example, the Kitaev model, quantum double model can be defined for Hopf algebras.
And that would correspond to Turaev-Viro with defects. And I mean, that exists also, but it's simply harder to describe. Like, I couldn't just say, oh, I take the group homomorphisms from the fundamental group of my manifold into a Hopf algebra. This would not make much sense. If it's like a Hopf algebra, then I would need to consider the integrals, and I simply don't know if I can get a fully geometric picture out of that.
Yeah, especially like these gauge transformations and so on. I don't think I don't know a simple way of describing that. But maybe eventually, I think maybe it can be unified by following the categorical approach. Like you have the fusion categories, bimodules, and so on. But then that's essentially like the Lemon-Venn or Turaev-Visual approach.
Yes, so I don't know how to say it. It's like one can do some things like with the Hopf algebras that make sense, like that you have paths and you assign to a path either a Hopf algebra, an edge, the Hopf algebra, or the dual. Then you can form the Heisenberg double and the Drinfeld double, and then you can consider something like the path groupoid, and you use the convolution structure of the Hopf algebra to combine it. But this is not so intuitive, and then you can have problems. For example, if you have paths that make loops and cross themselves again, and then you get messy things that are unpleasant.
Right.
So it's not so nice. So I'm not sure how to work this completely for Hopf algebras and if it can work. I mean, on the other hand, one has, of course, things like Cooper-Berg invariants. There you could argue it's also something similar, just it uses circles and it makes a Heegard diagram.
Yeah, exactly. Yeah.
So I think for the Hopf algebras, they're perfectly fine in the sense of you can do some defect TQFT with that or quantum double model with defects. And even for the data, it's not a problem. But what you cannot do, I think, is something that is immediately kind of geometrically basic and nice.
Okay. That's good to know.
But maybe one can, but I wouldn't see a way to do this. It's like, I mean, you can unify the Hopf algebra diagrammatic calculus, maybe with the diagrammatic calculus for bimodule categories, and then you get the diagrammatic picture. But I don't know yet how to formulate this in terms of fundamental groupoid.
Oh yeah, okay, I doubt.
Or even bundles. I mean, bundles are considered in non-commutative geometry, but this is not an easy notion. And I mean, they have the right concepts like bimodule categories or module algebras or co-module co-algebras. Like all these are concepts where I can see how they come up, but I cannot immediately make a link.
Okay. Are there any questions for Catherine? I'm going to stop the